If you have a smart dog, maybe you've bought them one of these geometric dog toys. They're quite lovely, with 6 different colors woven through each other in a symmetric manner. Here's a variation made of 6 stars, which bounces in more surprising ways, so dogs might like that. But what's the underlying geometry here? These are examples of regular polylinks, and are also called orderly tangles. Note that these have 12 pentagonal openings, like a dodecahedron. Here's another regular polylink. This one is made of 6 wooden squares, which again weave through each other in a symmetric, intricate fashion, but there are no pentagons here, so it's clearly a different structure from the dog toy. To make this physical model, I cut notches in these wood bars so they could snap together. Now to understand regular polylinks, let's start with the cube. Separate the 6 faces, rotate them all the same amount around their centers, here about 15 degrees, and translate them radially in towards the center. You have to imagine a magic material that passes through itself, so this is hard to do physically, but it's easy in software. I'll leave them in a position where the squares no longer intersect, and thicken them up a bit to snug them into their openings. Now, assuming they're no longer made of magic material, all 6 squares are fixed in their position with no freedom to move. Once I have a computer model, it's easy to build it out of plastic on a 3D printer. This didn't start as separate squares needing to be linked to each other. These squares were built from melted plastic in this linked configuration, just as you see it now. If you think you understand the idea, then test yourself by making a paper model of this version with flat squares. Cut out 6 hollow squares from heavy cardstock and assemble them. It's much trickier than it looks. Here I've used 3 colors to emphasize parallel planes with the same color. You can check that whenever 2 squares are different colors, they are linked, like 2 links of a chain. I only had to cut and tape back together 4 of these 6 squares. Now, let's generalize to other Platonic solids, starting with the dodecahedron. Again, we can separate out the faces, rotate them, and translate them radially through each other in towards the center until they make a weave. Notice that in this process we always maintain the rotational axes, the rotational symmetry of the original polyhedron, but we lose the mirror symmetry when we rotate the faces. Depending on whether we rotate clockwise or counterclockwise, we can make either one of 2 enantiomorphic mirror images. And here's a version of that in wood, again with lap joints. This is designed as a puzzle, and it's quite tricky to assemble. This process can start with any Platonic solid, so let's look now at a simple example based on the tetrahedron. With just the right rotation, the corners of the triangles hook through each other, and we get this rather lovely and sparse design. If the struts are the right thickness, they hold against each other and the result is stable. There's no freedom for anything to move. I find a ballet-like elegance in the way the components support each other. This structure has also been used as a commercial puzzle design. There are magnets in the ends of these wood struts, so you have to think about connecting north to south, but that's not the hard part of the puzzle. Visualizing the goal and keeping the first 3 triangles in the proper relative position before the 4th one is there to lock everything together, that's the hard part. So let's step back now and look at the big picture. This overall class of forms was defined and explored by the chemist Allan Holden. He examined the topologically distinct linkages you can obtain starting from the Platonic solids by rotating the faces and translating them radially. He called them regular polylinks and experimented to see what length of wood dowel was best for a snug fit. He gives a list in the back of his book of all the examples that he constructed. He also studied generalizations that he called orderly tangles. You might start with less regular polyhedra, or you might use star shapes instead of regular polygons, etc. Here, for example, is a 6-star design we saw earlier as a dog toy. Let's look at that design more carefully. How do we end up with only 6 pentagonal components? We're going to start with the dodecahedron and translate its 12 faces all the way to the center so they're concentric, and pairs that started out opposite are now coplanar. And then rotate the faces to the special angle at which they merge in pairs and become just 6 pentagons. This is another beautiful design. All the pentagons are equators. They project radially to great circles, and every pair is linked. No piece can be removed unless you either cut it or cut all the others. Maybe dogs like that. To make this design with rigid pentagons, I used aluminum bars with slots for half-lap joints cut at the proper angle. Again, it's trickier than you might think to assemble. In addition to the logic puzzle of figuring out the overs and unders, there's a dexterity puzzle of holding many parts in position before the final pentagon is in place to lock everything together. Now, for the combinatorics folks out there, let's quickly look at how the 6 colors are arranged in this toy. Everyone I've seen uses the 3 primary colors and the 3 secondary colors, but in how many distinct ways might they be assembled? There are 144 ways to make a cycle of 5 around an opening. That's 6 choose 5 to pick a set of 5 colors from the 6, times 5 factorial over 5 cyclic permutations. 24 necklaces, they're sometimes called. But only 12 of the 144 show up in any particular instance of the 6-color toy because it's based on a dodecahedron with 12 openings. So there are 12 possible arrangements of the colors. I wonder if anyone has collected all 12 different balls, and if so, is there a cool way to display them to emphasize their relations? So let's try an octahedron. Something wonderful happens here. Collapsing opposite faces together gives a symmetric structure of just 4 triangles. It's so simple and beautiful that several people have independently rediscovered it. Notice it has 3 fourfold axes of symmetry, 4 threefold axes, and 6 twofold axes, because these are all inherited from the octahedron. You can make the same structure starting from a tetrahedron because its planes define the same directions in space as the octahedron. In this case, we have a degree of rotational freedom to explore, but we'll lose the fourfold symmetry except at one special rotation angle. You'll find it to be another very good exercise, and surprisingly tricky, to visualize and build out of paper. Observe, by the way, that this is a different structure than the linkage of 4 triangles I showed made out of wood. In the wood case, the triangles aren't concentric because they aren't translated all the way to the origin. It turns out there's more than one possible tangle from any starting solid. Starting again with the cube, besides the one we saw earlier, there's also a more lightly linked example. It turns out there are 2 tetrahedral, 2 cubic, 3 octahedral, 5 dodecahedral, and 23 icosahedral topological varieties, not counting the extreme cases where the polygons are not linked at all or are merged into pairs. Robert Lang was the first to enumerate them all using a computer search. If you start with the icosahedron, the result can be pretty tangled, but there are 2 configurations worth looking at. One is if you collapse opposite pairs to get just 10 equatorial triangles. This simplifies things to be rather manageable. Here's a wood puzzle made of 30 sticks that assemble as these 10 triangles. It's lovely, but quite tricky to build. And a second very special configuration starts with the 20 triangles of the icosahedron and groups them into 5 concentric tetrahedra. This is the well-known compound of 5 tetrahedra, and here it's made of modular origami. So what are these regular polylinks and orderly tangles good for? Besides puzzles, they mainly show up in the world of sculpture. Several abstract artists have been inspired by them and incorporated them into works in some way or another. As one example, the woodcarver Bjarne Jespersen starts with solid blocks of wood and carves symmetric linkages of loops and knots. This takes enormous patience, often months of work for each one. I feel a little bad showing him plastic polylinks that I make in a couple of hours on a 3D printer. Another application is that for centuries, the structure with 6 equatorial pentagons has apparently been woven as a ball for the game that's called sepak in Malaysia or takraw in Thailand. The traditional rattan material is now replaced by injection molded plastic, but it uses the same arrangement of 6 equatorial pentagons. But puzzles, sculpture, and ball design don't really apply these structures so much as they display them. It's often observed that beautiful mathematics eventually finds applications. Lobachevsky is often quoted as saying, "There's no branch of mathematics, no matter how abstract, which may not someday be applied to phenomena of the real world." So, one of my motivations in making this video is to get more people aware of regular polylinks, with the hope that someday someone will find really interesting applications, or at least something deeper than a dog toy.